So I was working on this, to say the least, a little offline. Didn't want to capture all the hours I spent on this stupid one. I did come up with something that works, kinda, and I'll describe it for posterity purposes, but I doubt this is what is optimal. So, I went through a lot of different ideas about how to do the counts, some which you can possibly see, yeah, here, but what I ended up almost brute forcing was if I think about the restriction on the constraints here and the number of, I'll think of this as rows, or actually I'll think of this as columns. So if each column can only have 5 colors in it, there's a finite number of possibilities. Finite being something I can reasonably count. So if there's 5, then it ends up being, if there's 1, there's just 3 possibilities, right? Like red, green, or blue, or red, green, yeah. If there's two, then there's like 6 possibilities: red, green, red, blue, green, red, whatever, right? And then each additional column is a factor of 2. So it's 3 times 2 times 2 times 2 times 2. So it's like 3 times 2 to the 4th, which is 48. And then of those 48s, like every row has to be one of those 48s, and then every successive row has to be one of those 48s, because like literally there's no other possibilities. So if I were to treat those 48 possible rows with 5 colors in them, and there's like n number of rows, then I can treat it almost like a calculation of which of the 48 possible rows match which of the next 48 possible rows, and then do a count based on the number of ways to make those connections. So what ends up happening is first I do a raw calculation of how many possible combinations there are, and I literally make all the combinations using this for loop here. So like if there's 0 to 48 as your set of initial values, then you can take kind of the last digit of that plus 1 to make it like, if you do mod 3, it ends up being like a number between 0, 1, or 2, right? And you can treat that as the first color. And because I want it to be 1, 2, 3 rather than 0, 1, 2, I add 1 to it. So that's kind of the first color. And then I kind of remove that value from my combination, value. And then I treat this as, it's almost like creating digits on a number. So this is the last digit for this row number. And then for all the other digits, where the number digits is basically the number of columns. This is a pretty complicated formula looking, but it's, if you want the next digit is going to be one of 2 possibilities, so that's why it's val mod 2. And you don't want it to be the same as your previous digit, so you offset it to your previous digit. Mod 3 because you want to keep it within the range of 0, 1, 2, and then plus 1 so that it becomes 1, 2, or 3. So so that's the new last digit. and then again you're kind of building your row combination. So it's going to be row times 10 plus the last digit, and then you remove your that possibility from your value. And yeah, this took a bit of trial and error and checking to make sure this worked correctly. And then you append this to the number of row combinations that I have, and then I sort it. And just to verify like what it looks like, the row combinations for let's say two two combinations, or like two colors, is like 1 2 1 3 2 1 2 3 3 1 2, like colors being like 1 2 3, right? If it's 3, then it's like 1 2 1 1 2 3. So these are all the things that are 3 long with no adjacent colors or adjacent numbers be the same. And like 4, there's going to be so there's for 3 there's 3 times 2 times 2, so it's 12, and then 4 is 3 times 2 times 2 is 24. So anyways, for every one of these like 24 combinations is going to be matched with another combination, one of the 24 combinations on the following row. So actually, I mean, this problem, I relied a lot of kind of the logic and code for in the total characters and string after transformation part 2, which was a few days ago. So like here, there's the transition matrix, where the transition matrix is a square matrix which has transition matrix form to kind of connect row combinations that do not share color adjacency, do not share any color adjacency. How to spell this? Adjacency, adjacency with current, with last row combination, with current row combination. How do you spell adjacency? Is there no T there? Adjacency. Adjacency. Oh my god, so bad. Adjacency. Adjacent. Okay, maybe I was spelling that right. So that do not share any color adjacency with the current row combination. So for every index in the combination, and then for every adjacent or index for the other combination, I look at what the combinations are, call it other and combo. This could be a boolean, false or true, but this is just going to be same adjacency if it's 0 is false. Same adjacency being bad, being not connected. So if there's any colors that are matching, so same digit in the same spot of the two combination values, then I set the same adjacency to 1 and break. Otherwise, it's going to stay same adjacency as 0. If same adjacency is 0, then that's good, so it's connected. So I append 1 minus same adjacency. And then I append that to the transition matrix as a row, and then I need to transpose that because of the way that matrix multiplication works, you need to treat that as columns. Yeah. So I mean, I'll print out the transposed matrix, I guess. I think maybe I can print out the transition matrix to maybe describe what happened. Again, this is kind of not an optimal solution, so I'm not even sure if it makes any sense explaining this shit. But, so for instance here, so the row combinations are these 6 for 2 columns or 2 colors. And if you have, let's say, 1, 2, this is the first index, right? So 1, 2, if you treat that as a row, it can't connect to another 1, 2. It can't connect to another 1, 3 because the 1s are the same. It can connect to 2, 1 because the 1 connects with the 2, which is different, and the 2 connects with the 1, which is different. So that means that there's going to be a connection between those two. So so for this array, which is the connections for 1, 2, is connected to the 2, 1, and the 1, 2 is connected to 2, 3 because it's not the same in the corresponding digits. The 1, 2 is connected to the 3, 1, and the 1, 2 is not connected to the 3, 2 because they have the 2's in the same spot, or 2's are adjacent. So anyways, and then the next set here is the connections for 1, 3. The next set here is the connections for 2, 1, so on and so forth. And then you need to transpose that to do the calculation. And then once I have the transposed version, the vector itself, to denote that there's one of each possible combinations to start with, is going to be just 1 as a vertical vector, which is some row by 1 column. So that's this matrix. The number of times you need to actually do the calculation of the matrix is going to be the number of rows minus 1, treated as the power of the matrix, power of the transition matrix. Whoa. I just used the transition rather than transpose of it. I guess it works either way. I guess there's a bunch of asymmetries within this that you don't need to transpose it, probably. Yeah, I guess you don't need to transpose it. I actually think this is probably a symmetric matrix. But I'm not gonna care. I don't care. So maybe you don't need to transpose it. And then once you have your matrix multiplied by your vector, then you can just sum up the elements of the matrix to get your total counts. Again, all this is very similar to that other 3337 solution. Yeah. So, and then my answer actually is not very optimal in terms of speed, but I'm gonna go with it. So, summary. So, as number of colors per kind of row is finite set, finite countable / creatable. In this case, it's n less than 5, less than or equal to 5. I decided to create create all possible combinations and um, create a transition matrix that connects row combo uh, to row combo that to row combos that do not share any adjacent colors. There's probably some way to leverage the fact that this is extremely symmetric. I it's just a would require more brain power than I currently have or ever have had. So and then use transition matrix as to determine number of possible ways for n dimensions. So, which is going to be base take matrix to the power of n minus 1. And each time you multiply by the matrix, basically you're coming up with the counts for the number of ways to go from one row to one more row. And like the final answer that you get when you multiply these transmission, and you can also do, I did the optimization of taking a matrix power using fast binary exponentiation rather than multiply like 1,000 times the matrix, but it's like matrix to that power. But if I were to actually like print out what the answer transmission matrix when you multiply the vector is, it looks like the counts of each what's the reasonable one to look at? Okay, this is the answer matrix when you multiply the starting vector of all 1 combinations with the number of transitions. So what this represents is the last row of the number of times you have like 1, 2, 1 as the last row of your matrix, where your matrix could be of any of one of these starting combinations. And 4 is the number of times you see 1, 2, 3. 5 is the number of times you see 1, 3, 1, so on and so forth. And so if you sum up these counts, then you get the total number of possible matrices that could again have started with one of the row combinations. Obviously you take that with mod, and when you do the other stuff you have to do it using mod. Yeah. Okay. So yeah, this is hard for a reason. I'm not gonna. I don't know. I don't know if it makes sense to explain it that much more. Okay. Time complexity. This is gonna be O for my solution, anyways. It's gonna be O of O. So there's fast exponentiation incorporated within here. And if m is 5, then it's kind of fixed. So it's not really based on m. Actually, no. I hard-coded m is 5, but m could be longer, and it would take that long. So I think it's O of m n, no, it's not n, it's m log n, I want to say. I could be off about this. When you multiply two matrices, I think it's probably like mn log n, because I think, I'm not sure, I think matrix multiplication requires m by n computation, and fast exponentiation what is the matrix multiplication actually? Fuck. You're multiplying two matrices that are square matrix that have the size of 3 times 2 to the 3 times 2 to the power of m. Oh, okay, so this might be totally off, but so it's going to be size of transition matrix is on the order of 3 to the power of n. No, 3 to the power of m, where m is, in theory, whatever the lower is. Okay, 3 to the power of k, where k is the minimum of m and n. If it was swapped in terms of the constraints here, like if this m and n was like 1005, I would have swapped which one I used there. So size, so actually, let's say length of this transmission matrix is 3 to the k, and then you have where matrix is square sized k by k. So you would need to have that, and if you do matrix multiplication, would be, I think, k times k of k squared, and then you'd need to do that to the power, which is going to be log n. Matrix fast exponentiation. Fast exponentiation would be based on n, which is the maximum of m and n. So let's say fast exponentiation is log p, where p is equal to maximum of the other dimension. So overall, I think this might be O of k log p, where again, where k equals min of mn p. Oh, actually, this is squared, right? K squared. And p is equal to maximum n. This is all kind of garbage in terms of like my confidence in this. But this is probably what I would bullshit on an interview if I ever had to do this in person. And then space complexity, this is going to be O of you need your square matrix, so O of k squared where k is the min of mn. Oh, actually, the length is 3k, 3 to the power of k. Fuck. The length is 3 to the power of k. Technically, it's like 3 times 2 to the power of k, but 3 times 2 to the power of k minus 1. But the 2 is based on the 3. So, I mean, I guess maybe you can treat it more like 2 to the power of k. I don't know. Like, length of transition matrix is actually 3 times 2 to the power of k. 2 to the power of k minus 1. Where k is the min of this. Actually, I'm going to say that this should be, let's say it's s, where s is like the size. Okay, actually. One side of transition matrix is 3 times 2 to the power of k minus 1, where k is the minimum of mn. And when you do the matrix multiplication, it's going to be s squared. S squared computations. Okay. So this is actually s squared log p, where k is equal to, where s is equal to 3 times 2 to the power of k minus 1. K is the minimum and n, p is the maximum n. Space complexity here is again s squared, as above. And I think that's a wrap. I mean, honestly, I would look for other people to explain how to do this. I'm not the person that best understands or solves this one. I wonder if I should actually look up the solution to enlighten myself with the better coding techniques. I mean, I actually do wonder if there's a dynamic programming way of doing this. Okay, let's go ahead and maybe better myself. 0 milliseconds. That's fast. No data. Excellent. 2 milliseconds. That's fast. No data. Is there something wrong with my connection to the internet? What's going on here? No submission code for past time range. I don't know. Okay. It is what it is.